So, now let me briefly tell you the theoretical strategies, that one of the thing, fast phenomenological models, Mayer came later, but before Mayer around the same time, but after Van 't Hoff and Ostwald, we started doing we put these solute and solvent molecules on a lattice, because that could be solved, because I could now give epsilon AA, epsilon BB and epsilon AB just like we did in binary alloy, and I can count now how many ways I can put A and B. So, putting on a lattice has its advantage, and that was done in a great way in polymer by Floria Huggins theory, very famous theory which still plays a very important role in all studies of polymer solutions, even in ordinary solutions. This is very similar to Bragg-Williams approximation we did in quasi-chemical approximation we did in model. Then we have statistical mechanics, then the lattice model, which we will discuss briefly. After lattice model done, model we will discuss it. Then Nicolas description based, which will stretch theory. These are the famous things, Ornstein-Zernig equation, which we will discuss little bit, and then many other things we don't need to know now. But everywhere, remember, everywhere the main central issue remains the issue of the force fields. That's where osmotic pressure plays so important role. That gives you and that's what Floridi realized and used it in the polymer. And now we go to Floria-Huggins theory. Okay. So, as I said, when you put A and B together in a mixture, A and B together, then first thing I get is an entropy of mixing, and that is very well known is the entropy of mixing. Entropy of mixing per particle, I would rather take it out from here and put it here by N is Kb, XAL and XA. Kb is Boltzmann constant. So, XA is mole fraction of A, B is mole fraction of B. So, this is say B and this is my A. Okay. Say I have XAL and XA plus XPL and XB. These are the things by a mixture, comes from simple combinatorics. You calculate the Boltzmann omega number of ways from n factorial by na factorial by nb factorial. That is why lattice finds. So, n number of lattice sides and you are putting A and B together. It is very useful to get that. Now, so this is the entropy of mixing. Now comes things extremely important, which we have been talking, but we have not quantified, that how do I talk of AB, and I need something to say A and B different from each other. I need a quantification. That is done by this guy is discriminant. So, epsilon delta A, I introduce a term delta epsilon AB in terms of, now if epsilon AB is epsilon A plus epsilon B by 2, what is this called? Shubham, what is this called? This is Bartholomew rule. There is one more called geometric rule. Okay. So, if A and B interaction is just sum of the average of the, then you get the ideal solution, then you get Raoult's law. But that is not like water DMSO. You cannot say water DMSO interaction. By water interaction, DMSO interaction at the, because then the hydrogen bonding between A and B just disappears. Okay. So, the interaction between A and B brings a very essential new ingredient, and that is captured by this term delta epsilon AB. So, we call it discriminant, that how different A and B are in their properties and in their interactions, that what captures by it. This is Floridi, still we are doing all along Floridi. So, Floridi then said, okay, this is something we discussed a little bit, but if Z, which is in gamma in my Ising model, things is a number of your coordination number. So, in a lattice side, if this is my lattice side, then my coordination number is 4 in 2D, simple cubic lattice in 6D would be 6, 3D will be 6. So, Z is, so now I want to know that number of contacts between A and B, then I can say, okay, I pick up number of A there, then I can say, okay, the coordination number, and this is a very mean field, means average, and the mole fraction. So, that gives you number of contacts A, B, these also give, these two are exactly same quantities. Now, I have the entropy. I am doing all these things in order to do the enthalpy, and sure enough, once I know the contact, then I say okay, I can also write in terms of NA. It makes sense to focus on NB little bit more, because they are in our mind they are less in number, because B is the solute, A is the solvent. That is the kind of picture we have. So then NB is ZXA del V. This will be the enthalpy, because these are the contact. This is the number of contacts, and each contact brings a discriminant. So the enthalpy of mixing is the change, delta H mixing is the change, like entropy of mixing is the change in entropy. This is a new thing that comes in, okay, which was not there because of mixing, and that is delta H mixing. So now I add the two, enthalpy and entropy, I get the free energy. Now Floridi defined the following parameter, which is famous as a Floridi parameter, which is this quantity chi f is number of coordination number delta epsilon AB by dimensionless quantity. This is no dimension. Then we get delta H mixing. Now this term we are going to rewrite in terms of just introduce this z into delta AB, combine that, divide and multiply by KBT, and then we get this thing, the delta H mixture. Remember, now we have explicitly the Floridi interaction parameter or Floridi parameter. Now I get the free energy of mixing. I get the free energy of mixing by doing entropy term and the enthalpy term, and lo and behold, I have this beautiful thing. Now I have a elementary theory. I am not yet connected with osmotic pressure. That is my goal. I will do that. But now I can start saying some little bit more teeth into my understanding of physical chemistry, the phenomenology that we did in the undergraduate. And that I already told that. Now I want to say if they are structure making or structure breaking. If they are structure making and structure breaking, I will be able to tell them in terms of Floridi parameter, because if Floridi parameter is their negative, then it is structure making, because they like delta, they like each other more, they are more negative, but structure breaking is the Floridi parameter is positive. So suddenly I am beginning to have little bit of sense of structure making and structure breaking, and I can now begin to see if I can have some idea of structure making and structure breaking, then I can put them into a statistical mechanical theory. So from this structure making delta epsilon AB, if I can make an estimate of that, then I can take it over to my Lennard-Jones parameter, and I can do a statistical mechanical theory. Okay, now Floridi now said that in case of polymer, I am not going to go into details of that. Into polymer, what Floridi showed, that this number that goes in here, this number and these volume fraction. So number of contacts that we have done in A and B depends on the volume fraction. If one guy is much bigger than the other, then you have to talk of the volume fraction, and that is then goes into this. We will derive these things when you do the polymer theory of polymers. But right now I am just going to quote it, that because this is a beautiful work of Floridi, that this same thing goes over in a much more powerful and direct way, where Floridi parameter becomes a really powerful parameter to talk of ferrous solvent and many properties of the properties of the polymer solution, because solvent is so small and polymer is so big. That interaction between effective interaction between solute and solvent becomes very important. Please remember the term effective interaction, and we will come to that. But what Floridi parameter is trying to do is an effective interaction, and we will come back to that again. Okay, but before that, I want to this beautiful theory. The delta in mixing for a polymer is, you instead of you have volume fraction, but you have the mole fraction of solvent, but in case of solute, the polymer, it becomes the volume fraction. This I can trivial thing, but this is not that trivial. Okay. So, now I want to do, before going on, I want to connect the that we have done little bit in the Ising model, how these two models are the same. So, I now say spin up is equivalent to a particle A, spin down is particle B. So, in a lattice site I have a spin up, that means I have a particle, if spin down I have a B particle. So, when A interaction is spin interaction, that if it is favored ferromagnetic interaction, then epsilon AA is more negative, epsilon and BB they like each other. If I can tune these things of course, and A and B do not like each other, then that is up and down spin, they do not like each other. That is again the ferromagnetic interaction. If down spin like each other, then that is called anti-ferromagnetic interaction. That is also a very well known thing. But the main idea is that, see, part of Ising model, if you remember, doing after making all the approximation, after those 5 variables n plus, n plus plus and n plus minus, n minus minus and n minus, eliminating all these things by 3 conditions of the bonds of nearest neighbors, we get n plus n plus. Then we did a combinatorics after making a Bragg-Williams or quasi-chemical or whatever mean field approximation. So, here now I do exactly the same thing. I write the binary mixture energy as just like I do epsilon A, NAA, these are the NAR contact, NBB, NAB. So, just like there I have N plus plus, this is N minus minus, this is N plus minus. So, now just like in model we have these 3 conditions. So, the same as 5 variables become equal to 3 variables, the exactly same thing goes over. We will not know, as the total energy can be written in the following fashion by eliminating all the other variables, keeping AA and A. This is our NA is N plus plus and NA is N plus. So, same as before, we do not have to do an extra work now, or everything has been done by Bragg and Williams. We just map it into and use the free energy, that exactly happens. So, here is the given the A between them, connection between them, N plus is Na, then N plus plus is NAA here, and then energy of the Ising model is this quantity, and that we did in the Ising model class. Remember the factor of 4, the 2 and this quantity, except Z is gamma in Ising model. I am sorry about the change of notation, but Z is very common in polymer literature, and while gamma is quite common in Ising model. So, they are the we went by the kind of Z also used in Ising model, and that is coordination number. Actually, chem is like Z more, and however physics is kind of gamma is the nearest neighbor interactions. Partly came probably from Carson Wang on the famous textbook of statistical mechanics. But main thing is that there is a complete isomorphism between them. As a result of that, we can now write down the free energy. So, write down the free energy in the case of Bragg-Williams approximation. This was the free energy, wrote down that free energy in the presence of a magnetic field H is this quantity. Now, here the free magnetic field H, of course, we are doing magnetic field H equal to 0. So, this is for H equal to 0 or our B equal to 0, this goes over, and this is the expression, the equation that we need to solve, and epsilon here is epsilon AB. So, we get the solution of binary mixture by implicit. That has the beauty is that now, so the Ising model mapping allows us to explain very important this phase separation. Of binary mixture, wonderful. That means we need not do any extra work, but we realized that it is an isomorphic problem. this wonderful realization was done by Physical Review 1952. Two wonderful papers where this did and lattice gas, many other people, and it was done also by Guggenheim. I should not give only of name, the other person who do. And here is a beautiful book, Theory of Solutions, Guggenheim. Beautiful book, and that all the students should really go through. I was really fond of it. It's amazing how these days students don't learn any, I should not really start cribbing about it, but I find that there is much less enthusiasm in going and read because of the internet probably, and because of the everything at your desktop, all the world is coming to you at your computer. But in our time we used to go and advantage was that we used to discover many old books, many classic books like the Guggenheim books. There's one book by Fowler and Guggenheim on statistical mechanics, wonderful book, and another is Guggenheim Theory of Solutions, where he does the quasi-chemical approximation. Actually, quasi-chemical approximation was done irrespective of the Ising model by Guggenheim. I think I understated and underestimated the contribution of Guggenheim. So, theory of solution, and then it was found by T.D. Lee and C.N. Young that they are exactly the same. And but Guggenheim did a quite took the force in solving the quasi-chemical. The quasi-chemical name was given by Guggenheim, okay, and Bragg-Williams was done in Ising model. Quasi-chemical was done by Guggenheim, and these two are the same. That was shown later by T.D. Lee and C.N. Young. Okay, I think it is important to know this history. Okay, now the last bit we will try to connect now the importance of the osmotic pressure. And so I said that the osmotic pressure is so important, something not realized in physical chemistry books. Just give the applications of osmotic pressure, osmosis, then there are all other biological applications and chemical applications. But for a stat mech guy who is trying to explain binary mixtures and non-ideality and phase separation in binary mixture, spinodal decomposition and many other things, we need the force field, and this a measure of the force field comes from the osmotic pressure. That's the absolutely gold mine. And so we already did osmotic pressure. Now we kind of connect it together to do. And so the basic idea now is that I want an effective interaction, which is so important in polymer in every possible way, because this is called implicit solvent model. That means we remove the solvent, we are left with only if A and B, and there A is numerous and small, B is little larger, then I can remove the A and take only BB. But now the BB interaction is not the pure BB interaction, because it is mediated by A and B. It is mediated by A and is actually a very different beast. How do we do that then? And how do we get an estimate? This is what was done by this great theory of Macmillan and Mayer. Really wonderful theory and a very sophisticated theory. So what Macmillan and Mayer did, Macmillan was a student of Joseph Mayer, and they mapped this problem in a very beautiful and very formidable theory, very difficult theory. In our book, the StatMech book by Bakchi, we have, this is what a major thing that was done to really bring home the point. Okay, so Mayer's theory, we did that interaction potential as in a binary mixture. If I do a Mayer's theory, then it would be UAR, UBBR and UABR. This would be done. Macmillan Mayer now said, okay, I'll use Mayer theory, but I'll eliminate out A and I want to get that. If I can get that, then I have an effective interaction. Now, if I can have a virial series of osmotic pressure, my second virial coefficient will have the interaction between B and B. I hope, but that is I am talking about flow chart, and in the flow chart, how to get the effective interaction. So, the basic Macmillan theory with osmotic pressure gives me this quantity, which is very important quantity that explains the structure making, structure breaking, all non-ideality and these kind of things. So, this is a flow chart, I hope you can read it, that integrate out solvent molecules to obtain solid on the system, solids interact with an effective potential WR, perform Mayer's cluster expansion, and then once you do you get this beautiful, C is the concentration now or the mole fraction, you get the second virial C. So, the osmotic pressure, you have a virial expansion of osmotic pressure. So, what you have is a virial osmotic pressure pi, which is the concentration dependence. So, now I can vary the concentration, I can vary of course temperature, and I can now get this B to T, and then I can measure again with an effective interaction some form I can use, and I can get that. So, the isomorphism continues. Macmillan-Meyer theory is a very difficult theory. It is again given in my book in quite a detail SM by Bakchi. We will have quite a bit of that, but you are welcome and invited to do this. Is very important. I write 19 now and then, just shows that where I spent much of my life in the last century. So, this is the Meyer's virial expansion, and this is the Macmillan-Meyer, except these are the virial coefficient we know, and this BMM as the Macmillan-Meyer virial coefficient. And then this was very important. Then what they did, what Macmillan-Meyer did, derive an expression for BMM and showed that it is exactly same thing. So, it is exactly it can be explained, virial coefficient can be expressed in terms of this GBB. So, interaction between. So, these quantities are the radial distribution functions. They kind of tell you A and B how A and B. So, now I want to know if this is my B and this is A, then how B's and A's are connected with this, these are placed with respect to each other in a random system. In a liquid, how A and B are arranged with respect to each other. This is of course fluctuating, this is continuously changing. So, we will have an average description, and that average description is provided by, average means it is still microscopic, time average description, an equilibrium structure. So, this G is a very famous thing in the theory of liquids or theory of disordered systems. One of the most important equilibrium properties, these are called the radial distribution functions or the partial radial distribution functions, and they form a very important thing of the structure of liquids. So, before we go any further, we will now go into do the structure of liquids little bit, and then we will come back. So, now as I said that in a very low temperature, A and B phase separate. If A and B do not like each other, how do I know that they are phase separated microscopically? I can say, okay, how many A is around B and how many A around A. Then I find in a locally phase separated, if A and B do not like each other, even at normal temperature, when they appear to be homogeneous, they might be locally micro heterogeneity is there. They will be locally phase separated. How do I know that? I can calculate how many radial distribution function, which gives me how many A around B and how many B around A, how many A around A, how many B. These are the radial distribution functions. These are these quantities. How A is the joint probability distribution. How many A is around A, how many B is around B, and how many A is around B. They give the time average structure of the liquid. And now if there, then I would know, okay, A and B will be lowest, and that is here. A and B, this is A and B, this is the lowest. And A and A is maximum number, that is A and A. Next is B and B. So, this is A and A is around A, then B is around B, and A, B are depleted. So, this is the way one would try to describe now a phase separation, structure breaking liquid or structure making liquid. Is this the way we will go into it? So, we will now we will go to the next class and try to construct and describe these radial distribution functions, or how this theory of liquids are built to do these things.